We search for life out in the galaxy in what we call the habitable zone, or Goldilocks zone, not too hot, not too cold. But this presumes alien life is carbon-based or needs water. Could we be overlooking worlds running on alternative chemistries? Today we'll be discussing the possibility of life based on ammonia, probably the most popular alternative chemistry for life that gets discussed, except for maybe silicon as a carbon alternative, and not just discussed in fiction but in science circles too, for many decades. Indeed, NASA has given this a lot of serious thought, such as the 2003 article from NASA Ames, Searching for Alien Life Having Unearthly Biochemistry, written by Harry Jones, which we will borrow from today. The topic of if alien life might exist in the cosmos inevitably leads us to wondering how it might be different from it having arisen on strange new worlds unlike our own, and how this should change our methods for seeking it. Right now, we basically seek out life in what we call the Goldilocks zone, not too cold, not too hot, just right. But unlike in the story of Goldilocks and the Three Bears, we're not talking about porridge but water. A world covered in ice or in which the oceans would evaporate away is not a place where we'd expect to find complex surface life on. In the absence of surface life, we would not expect a rich ecology powered by sunlight, but life might live deep underground or in the deep ocean even if the surface of a planet was frozen over, and we discussed that option before, most recently in our episode on Hycean planets and ice worlds. However, it still assumes life is based on water, and there are some very good reasons to think that would at least be the norm for the universe, and maybe the only option. We'll be discussing that reasoning for today, and we'll be examining the possibility that ammonia might be an alternative basis for life, and critically, why it might make a suitable alternative to water. I want to emphasize that we're not talking about ammonia here as an alternative to carbon, as in carbon-based life, but rather as an alternative to water, as the solvent that all the chemistry of life is happening in and with. We are carbon-based life forms, but we have a lot more water in us than carbon, and we're discussing ammonia today as an alternative to that water. Carbon may or may not need an alternative in ammonia environments too, of course. You'll hear folks say we are carbon-based and suggest silicon as an alternative, and we discussed that a bit some years back in our non-carbon-based life episode. But it is important to understand that carbon is only the second largest fraction of mass in your body at 18.5%, while oxygen and hydrogen make up 65% and 9.5% respectively. That's by mass, and 93% of the typical human or animal is made up of those three. Indeed, hydrogen, the most common element of the universe, is the most common in our body too, as hydrogen atoms outnumber every other atom in your body combined. It's just that it is mostly as water, which is made of 2 hydrogen and 1 oxygen atom, and while hydrogen only has 1 proton and 1 electron, normally, oxygen normally has 8 protons, 8 neutrons, and 8 electrons, meaning 1 in 3 atoms in water are oxygen, but they make up 89% of the mass. When we start talking about alternative chemistries for life other than our own, it is critical to know how abundant and available elements and molecules made from them are, and not just inside our bodies. Phosphorus, the last of the big 6 elements in terrestrial life at 1% of our mass, is far less abundant than the other big 6, oxygen, carbon, hydrogen, nitrogen, and calcium, but it is around enough to be available for life to harvest and concentrate to the levels they need, and that would work for other rare elements. But where water is concerned, its abundance is critical as a solvent. Essentially, you need something for all the chemicals to dissolve in and interact with each other, and that's the role that water plays. And water plays that role very well. There are tons of solvents out there in nature, but there's a reason why water is called the universal solvent. More things dissolve in water than anything else we know of, at least when it's a liquid, not an ice cube. It's also insanely common, being made of the first and third most abundant elements in the universe, hydrogen and oxygen. Oxygen is a distant third too, far behind hydrogen and helium, making up only about 1% of the mass of the universe, ignoring dark matter, which is why gas giant planets are huge, but rocky ones made of oxygen or icy bodies are relatively small. They are left over after most of the hydrogen and helium fly off into space. Indeed, oxygen is typically the most abundant element on any planet or planetoid not cold enough or massive enough to hold on to hydrogen and helium against forces that strip lighter elements off the planets. When it isn't forced, it's usually a close second on something like iron or silicon. To come up with alternatives for life, we begin by either contemplating different chemistries that might work with water, or we contemplate options that replace water with another solvent, and that's where ammonia comes in as a potential alternative to water. First, it is very common. Most icy bodies we refer to are made of a mix of water ice, but also methane and ammonia. That's not surprising. Methane is 1 carbon and 4 hydrogen atoms, and carbon is the 4th most abundant element, about half as common as oxygen, just under 0.5% of the mass kicking around in space. And in methane, 75% of the mass is carbon, but 80% of the individual atoms are hydrogen. Nitrogen is decently common too, but around 1/10 as common as oxygen and 1/5 as common as carbon. Ammonia, being 1 nitrogen atom plus 3 hydrogen, is also fairly common. And as we see here, water, methane, and ammonia all represent very basic mixtures of multiple hydrogen atoms, the most abundant kind, with 1 atom of the more common elements, oxygen, carbon, and nitrogen. So all are abundant, whereas something like mercury, the quicksilver liquid on which rock can float, and which would not boil on all but the hottest planets, is just not very common, and maybe more importantly, would not be the dominant liquid on a planet where water could exist. Indeed, we often have lighter elements turn molten and float on top of mercury on any place where mercury might conceivably be common, but water couldn't exist. But ammonia is very common and is a liquid when water is not, freezing not until reaching -78 Celsius or -108 Fahrenheit. It is also a good solvent, not the equal of water in some respects, but better in other respects, such as being able to dissolve metals. It also has a lower viscosity, making it a better medium for movement of ions. But critically, ammonia is a vastly superior solvent to frozen water, so on colder worlds it's abundant enough to take over that role. Water ice, while likely to be very abundant compared to that ammonia, forms the ground on which a lake of ammonia might exist, as ammonia has a density of 0.73 kilograms per cubic meter, versus 0.9 for water ice and 1 for water. However, water ice is soluble in ammonia, so in that case, the lake might dissolve the underlying ground, and you would end up with a eutectic mixture rather than pure ammonia. Another issue though is that frozen ammonia is denser than liquid ammonia at 0.86, thus ice cubes of it would sink in ammonia, rather than float the way water ice does in a glass of water. No ammonia icebergs on a sea of ammonia, though it is less dense as a liquid or solid than water or water ice are. Life based on water and in water has the advantage that water self-insulates, freezing from the top down, allowing water to exist even on the other side of that ice, and the temperature may have fallen to fall below freezing, which is handy if you have significant periodic temperature variation on your planet's surface, from daytime and year length. This is potentially a big issue with ammonia lakes. I have heard it discussed as a requirement for life on Earth that ice be less dense than liquid water. Ice, the solid form of water, will float on it, but many solids are denser than the liquid they are frozen out of. Water's properties in this regard also encourage ocean currents, which might be more difficult for ammonia. A workaround might be where ammonia and water both exist. The water might freeze and float and insulate the lower ammonia-rich layers. A very great deal depends not just on the composition of a planet, but its average temperature and how that temperature varies from factors like day or year or latitude or depth. Temperature ranges on planets are not evenly distributed. Most of the bodies in the solar system are far too cold for liquid water to exist on the surface, or often even some underground pocket. It's not a case where planets gain twice as much sunlight have twice as high a temperature. Things in nature tend to reach an equilibrium point on their upper layers where the sunlight coming in gets absorbed and re-radiated as infrared waste heat at an equal rate, and will warm or cool till that equilibrium is reached. But that goes with the fourth power, as a first-order approximation. Earth has an average temperature of 288 Kelvin, just 15 Kelvin above water freezing. Ammonia freezes at 195 Kelvin, so a planet on average 15 Kelvin warmer than that would be 210 Kelvin. That is 73% of Earth's average absolute temperature. That would imply it only got 28% as much light as Earth, about what we expect from an object twice as far from the Sun as us. Past Mars, but in from the asteroid belt. Let me emphasize that was on a first order approximation, and other energy sources like leftover heat of formation, radioactive decay in the core, and tidal heating have way bigger effects proportionally on keeping that planet warm as sunlight diminishes. What it basically means though is that a planet like Earth could have seas of liquid ammonia while still being close enough to its sun for us to imagine photosynthesis or some other solar-powered pump for life operating and permitting a robust ecology. Ammonia is also a good heat reservoir, even better than water, making it slower to rise or fall in temperature. Clouds of ammonia and ice of ammonia are both white, like water, making them more reflective to incoming light. I suppose strictly speaking that the ultimate medium for stable life temperatures would be very reflective when as hot as cloud vapor and opaque and absorptive as an ice. Atmosphere on a ward of ammonia seas, even colder ones, would have a fairly high percentage of ammonia vapor, as an analogy to water vapor and humidity, as ammonia has a high vapor pressure, though that can be a downside too. The hydrogen bonds in water are stronger than ammonia, and that affects not just vapor pressure, but also surface tension of a liquid and how hydrophobic or hydrophilic other chemicals are to it, the ammonia equivalent of that. There are doubts as to if very simple early life could hold itself together well enough to allow a self-reproducing system. Titan, Saturn's biggest moon and with an atmosphere thicker than Earth's, might be a good place to get a look at what chemistry goes on in ammonia-rich environments, and speculation that Titan might hold life is often assuming ammonia-based chemistry. Using Titan as an example, there is a decent chance that these worlds would have thicker atmospheres on account of being colder and farther from their suns, even if much closer than Titan, which might help protect the ammonia from UV, and it's possible that photochemistry could produce a high-altitude haze analogous in function to ozone, but these worlds would still fare better around lower UV stars, which conveniently are the majority of them. Our sun is one of the biggest and hottest 5% of stars, and thus releases a larger share of its light in the blue, violet, and ultraviolets than cooler stars do, which are stronger in oranges, reds, and infrareds. It is harder to speculate on colors. By default, we would expect the same blue skies as Earth gets, with the same reddening at dusk and dawn, perhaps slightly more reddish if there is indeed a protective high-altitude haze. Ammonia is a better solvent for alkaline earth metals, which might become the equivalent of salt in their equivalent of saltwater oceans, so you might get seas of ammonia with a gold or bronze shade to reflect those alkalines while fresh ammonia remains blue. Nitrogen is plentiful in Earth's atmosphere and would be expected to be on an ammonia-heavy world too. It is harder to make the case for free oxygen in the air since ammonia is flammable in oxygen, though nitrous oxide ought to be plentiful enough. As a caveat though, ammonia is not super flammable like gasoline, which will burn when it's at a concentration of just a couple percent in the air, but in the 15 to 28% range, more like carbon monoxide. Alternatively, water vapor is only a few percent normally too, so ammonia at that concentration as a substitute for water would not be flammable. That is all dependent on overall pressure and ratio of oxygen in that air too. Still, I wouldn't be too optimistic about ammonia and oxygen both being in larger concentration in an atmosphere, but we probably don't want to casually rule it out either. Additionally, it may be that life on terrestrial planets based strictly on ammonia rather than ammonia water solution would be more likely on so-called carbon planets. These worlds are speculated to form around stars favoring carbon over oxygen to the point that rocky worlds are based on carbides rather than silicates. Such worlds could have seas of ammonia without necessarily also having lots of water ice around. Early worlds would likely have lots of various hydrocarbons around though. We think a case can be made that vegetation on these worlds might be dark or black as opposed to green. Unlike water worlds like Earth, plants on ammonia worlds may not need to deprotonate water or ammonia molecules to get an electron for photosynthesis. This is because the dissolved alkaline earth metals release solvated electrons that can be used directly. This could free up photosynthetic plants to use a wider range of the spectrum. Nonetheless, we're not really expecting dense life like we see in rainforests. Many alternatives to water have been proposed, but ammonia has remained the strongest candidate since J.B.S. Haldane first suggested at a symposium back in 1954. One of his strongest points is that a lot of water-related organic compounds have ammonia-related analogs. These could serve as a basis for life. One objection to ammonia, and there are plenty, is that it has a lower range of liquidity. Water has a 100 degrees Celsius or Kelvin or 180 degrees Fahrenheit range of being water at normal pressure. It's a good deal higher at higher pressures, while ammonia's range is smaller, only about 44 degrees Celsius or 80 Fahrenheit. It boils at a mere negative 33 Celsius or negative 28 Fahrenheit, and freezes at not much less, and if you're wondering, the ammonia you use at home is usually mostly water. Ammonia mixed into water is a great antifreeze solution. I suppose we might contemplate life based on ammonia-rich water, or which existed in one state in pure ammonia, and as the planet warmed in the summer, an ammonia-rich mixture of water, but in truth I don't see the temperature variation mattering much. Water is liquid from 0 to 100 degrees C, but few lifeforms can exploit the upper end of that range. Proteins can be damaged at temperatures significantly below the boiling point of water. That might be less of a problem for ammonia-based lifeforms. In fact, a bigger problem might be molecules being too stable for metabolism at liquid ammonia temperatures. Also, since liquid ammonia does not expand as it freezes the way water does, freezing might not be fatal for ammonia-based organisms as it is for us. Freezing in the wintertime and thawing out again in the spring might simply be part of their life cycle, so the habitable range of temperatures in ammonia might not be much less than it is in water. We also probably do not want to assume the pressure is the same as on Earth. Substances usually have a wider range they are liquid at higher pressures, and lower when the pressure drops, to the point that you can't really have liquids in a vacuum or near vacuum. Temperatures vary less when you're colder. Pluto, for instance, varies from negative 233 to negative 223 Celsius, a mere 10-degree difference. And while there probably are higher and lower spots, Pluto is not explored much or in detail, there's just not much room for temperature variation, even though its high eccentricity means it gets 275% more sunlight at perihelion than when it's furthest from the sun, aphelion. There's no liquid ammonia on Pluto's surface, of course. We're talking about worlds considerably warmer for ammonia oceans, even if frigid compared to Earth, but there's definitely ammonia on its surface, and there may be liquid ammonia pockets below the ice. Indeed, Pluto has cryovolcanoes that we think erupt an ammonia water mix onto its surface. As for ammonia worlds, their atmospheres are likely to be rich in ammonia and methane, which are greenhouse gases. This may help to further moderate temperature extremes. It may be that some ammonia worlds can remain within ammonia's liquid range even at the poles, especially if air pressure is higher, expanding that range. NASA aims increasingly views ammonia as a biosignature to look for, since it's such a key ingredient in life-based chemistry and so short-lived in the presence of ultraviolet. So finding it on a planetary surface like we have on Pluto strongly implies activities depositing it recently or regularly. Not necessarily life, of course, but it implies active cycles and churning going on below, and where you've got motion and activities in liquids, life becomes a lot more plausible. On the more general topic of searching for plausible alien life locations that are not very Earth-like, and speaking of NASA aims, I mentioned a short article on alternative alien chemistries they did in 2003 near the start of the episode. In that paper and a previous one, 20 basic principles of extraterrestrial ecology, or exoecology, are summarized under 5 general areas, and I'll quote those now. We have 5 categories, each with 4 principles under each of its headings. Those categories are environmental interaction, ecosystem design, ecosystem dynamics, material cycling, and temporal cycles. Let's run through those and then we'll boil it down, both in the case of ammonia and generally, and I'll interrupt the quotation occasionally when it is using a term that might not be obvious to the casual listener. Category A, environmental interaction. A1, the exoenvironment will limit the potential types of exoecology. A2, different exoenvironments will support different ecosystems. A3, the exoecology will be adapted to its environment by evolution. A4, the environment will be affected by any exoecology, which boils down to saying alien ecologies are limited to what alien environments permit, but likely to have some diversity, such as Earth does between poles and tropics, seas and land, and that life there will adapt to those environments, and those environments will be altered by that. Things change when plants arise and change the plant's albedo or reflectivity, alter the atmosphere makeup, and bigger critters like beavers start making dams and so on. This is all important for basic consideration, but also be mindful that when looking for astronomical biosignatures, we may take for granted they will exist, as the planet will be changed by life being on it. Category B, Ecosystem Design. B1. An ecosystem will require energy input and use material recycling. B2. An exoecosystem will contain a trophic food web of producers, decomposers, and possibly primary and secondary consumers. B3. The number of trophic levels will be 4 or fewer. B4. An exoecosystem will have an hierarchy of compartmentalized subsystems. Or essentially, life needs energy, needs to be good at using it and recycling elements, and that, as a result, it tends to include components that do that recycling, which means eating each other, eating waste, decomposing waste, and so on. Trophic levels are basically the food chain. Level 1 are primary producers like plants. Level 2 would include herbivores that eat those plants. Level 3 are carnivores. Level 4 are apex predators. And we usually talk about food webs these days, as nourishment can flow around in a lot of ways. Like we can eat plants, eat critters, eat carnivores, and even eat each other, and we can also feed all of the above. Category C, Ecosystem Dynamics. C1. The energy flux and storage will be an order of magnitude lower for each higher level of the trophic pyramid. C2. Higher energy flows between trophic levels will increase stored energy and ecosystem diversity. C3. Energy will be dissipated and converted to heat. C4. Energy is not necessarily the limiting factor in exoecosystem growth. How much energy a world is getting is a big factor in how big and complex these situations can be, and an ammonia-based world is likely to be on the lower end of that, though again you might have a photosynthesis analog on a colder world orbiting a dimmer star low in ultraviolet, but we're often assuming alternative cold chemistries like ammonia, or methane for that matter, are running on far weaker overall energy supplies, especially given that we often imagine them on smaller worlds like comets or icy moons. Or more of the SFIA K2 Dyson swarm style of conversation, larger megastructures with vast amounts of engineering at every level including genetic might be able to get away with more trophic levels. Obviously such megastructures are themselves signs of life of some sort. Category D, Material Cycling. D1. The material cycle will be closed by decomposers. D2. Material cycles with a gaseous phase will cause uniform distribution of the material. D3. Materials with no gaseous phase will have a more varied spatial distribution of the material. D4. Material availability may be a limiting factor in exoecosystem growth. All life eventually needs to be recycled around those basic building blocks again to be reused, or life won't last long. And factors for how well it works or how plausible a system is for permitting it need to contemplate what states of matter can be used too. So for instance, life made of big frozen blocks of matter, rather than liquids or gases, is occurring at a very slow speed. And Category E, Temporal Cycles. E1. Temporal cycles in exoecosystems can be caused by external or internal factors. E2. External astronomical factors may cause day and night, tides, and seasons. E3. Internal dynamics will cause exoecological succession. E4. Stable systems typically have only one limiting factor. And Category E we may boil down to saying that day or night or seasonal cycles are going to have a huge impact on how life operates in that environment and how stably it does so. Stable is good, though of course you also need some change and chaos to disrupt ecosystems if you want them to change, as otherwise critters get hyper-specialized to that niche, which you can argue would tend to limit it getting evolved to really impressive states like technological civilizations. More generally though, a world with constant crazy changes or really complex cycles, like a planet orbiting eccentrically around a pair of binary stars, which also vary themselves a lot in brightness, is not a place we think of as being super friendly for life to begin and dwell. In that same vein, we can look at a planet that's ultra cold and see the presence of liquid helium, and say that might be ultra low in temperature, but superconductors could run there and natural computers might form and thus have brains. But the timeline for anything happening with chemistry in that sheer cold is so immense that we wouldn't expect such life to have had a chance to emerge yet. Maybe long after the stars are born out, or in a different universe with factors just different enough that stars never really formed much or got as hot. And our 5 categories are less of a hard list on where life can or can't be than they are a reminder of what we need to consider when we do come up with an alternative option. Yes, a hot planet might have liquid mercury still, but is that abundant enough and concentrated enough to offer ecosystems? And what's that heat doing to those other categories? Not much complex chemistry with big long protein analogs seems very likely in that level of heat, and of course is utterly impossible inside a star, another place popular to contemplate life in science fiction, but not in astrobiology or exoecology, unless it was running on some exotic matter like mag matter or magnetic monopoles. And again, we can always find a what if or an exception, but as we run it through those categories, the realism of the situation gets iffier, especially when contemplating natural life as opposed to something we might artificially tailor to such places, which cannot be ruled out, of course. Life may never form on a place so cold it has hydrogen and helium oceans, but somebody may have created some, and the word life gets very ambiguous in a technological context too. Such a world might be home to an uploaded digital civilization enjoying the safety and computing efficiency of life under the liquid helium oceans of some rogue planet. But for our purposes today, the key thing is that while ammonia-based life definitely has some factors working against it, it does not break or push any of those categories. It is very abundant, and the worlds on which it might be abundant are also not something we would expect to be hyper-rare or dominated by some alternative like water, except possibly what we might deem an antifreeze planet, where the seas were ammonia-rich water varying in concentration by location and season. This, unfortunately, is the limit of our speculation. We would expect ammonia planets to be less abundant in life than water worlds, and probably an order of magnitude less common too, and likely as a result slower to evolve, so probably not a common chemistry among spacefaring civilizations in the universe. But in a galaxy of trillions of planets, should it turn out that simple life arises fairly often, even if intelligent life is a rarity, that many worlds have algae or slime on them, then I would say there's a good chance a small but not minuscule portion of those might be based on ammonia, and it might have some non-microscopic ecology too, though odds aren't great that a colder, slower world would evolve complex life. Of course, some red or orange dwarf might have had such a world circling it for 10 billion years at this point, so maybe they had enough time. And such stars will live for tens of billions of years to come, too. The good news for them is it might be easier to get galactic colonists to leave those planets be. We often imagine it being hard to quarantine worlds with very primitive life on them, that after you find enough examples of alien algae and bacteria without anything even as complex as an insect on them, you stop trying to keep people from settling them, even if it ruins that local ecology. But a planet so cold it makes Antarctica look toasty probably would not be as high a priority destination for most colonists, even if it didn't stink of ammonia and have an atmosphere that would burn if the oxygen from your habitat leaked out and sparked. So whether or not there's life out there based on ammonia chemistry, it's not likely to be a popular tourist destination for folks from Earth. So we were talking about alternative chemistries that might support life today, and I know one that definitely works, and that's coffee. It's the substance that's kept this show running for 9 years now, and has been the drink and a snack I always refer to in the show. And also the better part of a decade in the Army, all my time as a physics major in undergrad and grad school, and actually all the way back till I was 4 years old. Coffee is the fuel that keeps civilization running, and if you like your coffee, there is no reason not to be picky about it, to find that brand that's perfect for you. And that's why I'm very glad to tell you about our new sponsor, Trade Coffee, that connects people with nearly 500 different coffees from roasters around the country to ship you fresh roasted coffee. Upgrade your morning routine with better coffee. Right now, Trade is offering our viewers a free bag of coffee with any subscription at drinktrade.com/IsaacArthur. Discover new craft coffee with every delivery, with free shipping, customizable plans with coffees curated to your taste with the help of matching algorithms. For me, that appropriately came up as Space Cadet Coffee from Atomic Roasters, which was a perfect blend for smooth cold brew with great flavor. Enjoy hassle-free coffee, always shipped within 48 hours of roasting, and treat yourself to some new brews. That's drinktrade.com/IsaacArthur for a free bag of coffee with any subscription purchase. drinktrade.com/IsaacArthur. As a quick announcement, tonight, July 20th, 2023, the National Space Society will be having its weekly online space forum, and this week is a town hall meeting with the NSS leadership, including our CEO, Anita Gale, our COO, Dale Scran, and myself as NSS president, and many others covering objectives and goals for the NSS in the near future. It's free to attend and you don't have to be a member. I hope to see you there, and I'll link it in the episode description. So that will wrap us up for today, but not for July. Join us next Thursday, July 27th, for a look at the future of warfare with dropships and planetary invasions or boarding actions. Then that weekend, on Sunday the 30th, we'll have our monthly live stream Q&A. After that, we'll head into August to look at building a space elevator not on Earth, but on the Moon. Then we'll head trillions of years into the future to the end of time and the final twilight on the last planet. Then it will be time for a monthly Sci-Fi Sunday on cyborg armies. And if you missed this weekend's Sci-Fi Sunday, Robots and Warfare, you can catch it now while you wait. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.